Okay, welcome to the second video about electric potential for AP Physics C. We'll be looking at the idea of equipotentials here and the relationship of potential to field. Now, recall in the last video we defined the electric potential as the negative integral of E dot dx, where dx is a small distance element. Or, strictly speaking, that's delta V. And we said that V is equal to 0 at infinity. So that's how you get the potential from the field. Now we need to look at how you get the field from the potential. And we see that potential is the integral of the field, and that means that the field is the derivative of the voltage, or the potential. Specifically, the x component of the electric field is the negative derivative of V with respect to x. The y component of the field is the negative derivative of V with respect to y, and the z component of the field is equal to the negative derivative of V with respect to z. Now that's actually a vector calculus operator known as the gradient, but you don't really need to know that. What you do need to know is that to get a component of the field, you take the derivative of the potential in that direction. An example here, this is problem 32 in your textbook. The electric potential in a region of space is given by V equals 1500x squared, where V is measured in volts and x is in meters. We need the magnitude and the direction of the electric field at 1.3 centimeters. So to get the x component of the field, it's negative dV dx, which is negative 3000x. If we calculate that at 1.3 centimeters, that works out to negative 39 newtons per coulomb, or volts per meter. Now, because the potential does not depend on y or z, the derivatives with respect to both y and z are 0. So the y and z components of the electric field are 0. The x component is negative 39, so we would write the electric field like this, negative 39 newtons per coulomb I hat. Now the other thing we're going to be looking at in this video is the idea of the equipotential. This is review from last year, but what it is a set of points that all have the same potential. So it's kind of like the lines on a topographical map. Those lines are the sets of points that all have the same altitude. And so let's say you've got a point charge. Well, there's our point charge plus Q. All the points with the same potential are circles. And those circles start out closely spaced and get farther away. And the relationship to the electric field is, remember, the electric field is the negative derivative of the potential. And a consequence of that is that the electric field lines are always perpendicular the equipotentials. The idea is the electric field always points downhill. So for a point charge, the electric field is the red, and the equipotentials are the blue. Notice that every time an equipotential crosses a field line, the two are perpendicular. The other thing to point out is that the electric field points from high potential to low potential. That's what the negative sign in the derivative means. And so the potential is very high near the positive charge and lower farther away. Now if we look at the equipotentials associated with a dipole, remember a dipole is plus Q and minus Q. If we draw the electric field lines, and I'll use red again here, the electric field lines of a dipole look something like this. So if we draw equipotentials, we'll find that there is an equipotential there, running right down the midpoint between them. And if we draw other equipotentials, we get these kind of egg-shaped things, which get closer and closer to being circles as you get closer to the charges. And you have high potentials around plus Q, low potentials around minus Q. So this here represents kind of a mountain, and this represents kind of a hole. For tomorrow, I'm going to be looking at questions 6 and 7, and also problem 30. All of them deal with equipotentials and calculating field from the potential.